All right. Oh, perfect. Right on time. Right on time, guys. So, I would like to welcome everyone here to the June, actually the end of May, Mad AI event. We are like a May, so typically do once a month, and we had a really great opportunity to have a international expert come to Madison. And we are super excited to host Dr. Rocha, okay, from Brazil through IEEE. We got a chance to bring him in. He was coming in to give a talk up in the Twin Cities, and through fate, we ended up being able to bring him here, and we are super excited to have him. He is an international expert. He's been working in this field since 2001. He's got his PhD within the field, and like we chatted earlier, like our PhD work, I think, shared some random forests. So utilizing random forests for some machine learning aspects. So really excited. Like, got a chance to give him a tour of the campus and the city, a little bit of the city. But just really excited to have a great speaker today, and like as always, like this wouldn't be possible without IEEE. And please consider joining. If you're not, if you are a member, thank you so much. Like, your support helps make this possible. And without further ado, I would like to bring up our speaker. And so, how about we welcome him?
Thanks a lot.
Thank you, Anderson.
So guys, thank you for joining. The ones that will watch later, it's also nice to have you paying attention to these topics. I didn't know at first what would be the background of everyone here. So some of the parts I go into more details, some of them less, but if you have any questions, just let me know. Disclosure, this is about artificial intelligence and how we develop methods to solve some problems, in spite of some people saying that you can solve all the problems with AI. That's not true. And I selected two specific topics along with Chris for today. One is self-supervised learning, when the algorithms teach themselves. And then the second one is much more difficult, is about going from correlations to causation. So instead of finding what's correlated in the data, you want to find what causes what. Okay, so this is causality discovery. And as Chris said, I'm Professor Anderson. I've been a professor of computer science for 17 years. I'm a full professor in the University of Campinas. Here you have the University at Night. It is a Fibonacci series, as I was mentioning to some. At the center, you have the core areas of science, like biology and physics and mathematics. And as you go out of the rings, you go to the applied sciences. And of course, we are considered applied. So computer science is more to the outer part, okay? And Campinas is in the southeast part of Brazil. It has 1.2, 1.3 million people, and it's about 1 hour from São Paulo. And the region is known for being the Brazilian Silicon Valley. So out of the Forbes 500, about 80 to 100 companies are in this region, especially the ones in tech and biotech. So I prepared this as part of the Distinguished Lecture Series from the IEEE Signal Processing Society, and I thank you for welcoming me here today. As I said, I've been a professor for more than 16 years, and I created this lab. It's called Reasoning for Complex Data, Recod.ai. It's a lab that counts with more than 300 collaborators around the world, and in the university we are 9 professors fully dedicated to this lab, and we have many other collaborators spread on campus and also in other universities. So this is the lab, and as I said, we created it in 2009, And the idea was since the beginning to research what we called humanistic artificial intelligence, or if we consider more recently, it's also known as human-centered artificial intelligence. What it means is that we want to develop solutions for which the humans are involved. They help in the protocols for data collection, they help in the protocols for data analysis, for the algorithm development, and for the decision making. We don't want a method that takes decision just by itself without explainability, without audits, without the possibility of understanding what's going on. So this is what moves us in the kind of research that we do. And here are some examples of our students. We have research that goes from health and well-being, for instance, detecting early signs of diabetes, Parkinson's, or hypertension, stress, anxiety. But we also have research in disinformation, how to detect like when a document is forged, signature is falsified, when you have like someone trying to get your money and your credentials through a message in WhatsApp or Telegram or SMS. So this is the kind of research that we do. And today I'm going to give you some examples connected to the 7 greatest challenges of AI in the decade. So considering the key aspects that we have, the key challenges that we have in AI today, the first one is going from correlation to causation. So instead of knowing that variable A and variable B are correlated, I want to know if A causes B or B causes A, or they are just spuriously connected. Okay, and this is important because, for instance, suppose that you have a medical problem and then this patient is sick, and then the doctor comes and thinks that the treatment is this particular medication. And then the doctor gives this medication, and something happens here, but did this person improve or got worse because of this medication, or it was just like correlated? So this is quite important. And especially if this patient gets something like in a very bad situation, he dies. If this patient dies, if I had changed the treatment, would the outcome be different? That's the thing. So this is the first challenge that we have, a big challenge for the next decade until 2035. It's causality. And if you think of these models that we have, large language models nowadays, Claude and ChatGPT and others, they still don't understand in a general way causality. So the solutions that we have for causality, they are problem-driven. The ones that I'm going to show you, they are problem-driven. I'm not claiming they are going to be general. So at least if you can understand for a particular problem the causal links, that's enough. That should be enough for you to solve your problem. The second is self-supervised learning. Here we want to learn from big amounts of data without the need to have specific labels all the time. And sometimes you can do it, sometimes you don't. And I'm going to give you some examples. Then the third is about reasoning and planning, reliable long horizon reasoning, abstraction and strategy. The fourth is when you have an answer, it needs to be grounded. So a very important word that we have nowadays is grounding. So when you ask ChatGPT, for instance, something, and it gives you an answer, is that answer grounded? So is it based on facts, or it's a hallucination? So if it's a hallucination, then the answer is just like plain wrong or approximately correct. So you don't always know. Then 5 is about alignment and robustness, so building safe and truthful interpretable AIs. 6 is about doing this in a more efficient way, doing it cheaper with less computing resources. And 7 is how to develop these solutions with the humans involved. And all of these are connected. And today I'm going to give you some examples about 1 and 2. For the sake of being on the same page, I would like to define AI pragmatically as the ability of any computer system to get data from the world, interpret this data, learn from it for particular problems, and use these capabilities to solve specific objectives and tasks through flexible adaptation. What it means is that for us, AI is very well defined in terms of pragmatism. Get data from the world, organize this data, learn from it, interpret what's in there, organize what you learned, use these capabilities to solve specific problems, not general problems. I'm not talking about artificial general intelligence. And then you need to be able to adapt over time. Okay? So this is it. No philosophy involved, no humans being taken over, just engineering. And the first problem that I'd like to discuss with you is about self-supervised learning. The application here is just an example. We selected an application with our partners. We developed this project with DARPA, the research military agency here, and also the Brazilian government. And the idea was to identify suspects after, for instance, mass demonstrations with violence or fights with victims in a stadium, that you capture some images of the suspect through some cameras, but then you have dozens or hundreds of cameras and like hundreds of hours, if you sum up everything, how can you look for a specific suspect? And of course, you cannot have labels for this. If I'm looking at a person that I just saw right now, there is no way I can get labels for that particular person because it's exactly the person that I'm looking for, right? So everything here needed to be without labels. And we needed to do it fast because we wanted to process like hundreds of hours of videos. So this problem is called large-scale re-identification. And you might think that we could use the faces of the person, but we don't have the faces in a good resolution most of the times. So we need to use all of the body of the person to look for that particular person. So we have many complications. How to find the same person in an environment covered by different cameras. So you need to match the same person across different cameras. So you have viewpoint variations, you have illumination changes, you have interactions with objects and occlusion, and you have cross-resolution because you might have one camera here that's completely different from that. So one camera might be from a building, the other from the city hall, and it varies. So you cannot have like a standard way of putting together those cameras. So you need to be able to be robust to different cameras, different resolutions, different brands. And in addition to that, you can also sometimes, instead of looking for a person, you might be interested in looking at a vehicle. So you have like a bank heist, for instance, and the suspects like went away with a specific minivan. How do you find it quickly in hundreds of hours of video? So here it's you have these. You want to re-identify these vehicles, and for some of them you have like the latitude and longitude localizations. But then you need specifically to find where it is at that moment. So you start searching for all of these videos until you find the most similar vehicles that you're looking for. And some of these classification problems, they have also a strong semantic difference. For instance, when you try to separate a cat from another cat, which is like one of the important problems, so to say, in computer vision, right? People love to separate cats. In that case, you have like strong semantic differences depending the way that they collect the images. But this is not the case for the re-ID problem. The re-ID problem, it's a little bit different because we have interclass similarity. So many people look alike. And how can we differentiate that? And we wanted also to develop a solution that would be based on self-supervised learning, but you could just like get any other application and the basics, the mathematics behind it would work for the other problem as well. So since the beginning, we wanted to develop everything that I'm going to show you. We wanted to think of everything in terms of the vectorial space. So you wanted to work with the vectors so that if the representation of the image is a vector, if I switch it to the representation vector of a text, it would be the same. So as a second problem that we wanted to work with, we have the identification of the author of a text. Specifically, we wanted to identify the author of a post in a social media post. The case here, you have like typically 140 characters for X or 280 at most. And we wanted to capture the stylistic form of the author and the way that this author writes to identify if a particular person is the author of a given post. So we have like dozens of authors with dozens and thousands of posts, and if I have this particular post, I can ask, is it authored by this author, by this one, so we can do this test. So given two short text social media posts, were they written by the same author? So that was the question. So usually prior art solved these two problems in a supervised manner. From 2000 to 2015, so to say, most of the methods that we have seen in machine learning, they were based on labels. So if I want to detect if a person has a probability of having a heart attack, I would be based on several examples from medical exams with doctor annotation of like the medical record of that patient showing, okay, this is a guy with a heart attack history. This is a healthy guy that never had a history of a heart attack. And I would train a method for that. If I wanted to separate dogs and cats, I would have like hundreds or thousands of images of cats and dogs manually annotated, and I would separate them. But then, as of 16 or 17, people started asking, okay, but it's quite hard to have labels for complex problems. And if you need big data, you need a different way of training. For years, we've known that we could do it in an unsupervised way. But unsupervised, usually it's like not on par with supervised learning. So is there anything in between that we could work with? And well, we know that there is a semi-supervised learning in which you know some labels and then you can propagate those labels, getting like some advantages of the supervised learning and still being able to deal with large quantities of data. But still, it was not like on par with supervised learning. And then came along a new set of techniques called self-supervised learning. And the idea of self-supervised learning in a nutshell for you is this. Given an image, for instance, I don't know the class of this image by definition. But if I transform this image and generate another, suppose that I get this image and I rotate it a little bit. So now I have the original and the one that's slightly rotated. And then I can also have one that's like cropped like 5%, and then I keep like 95% of the content. So I have three versions now. I don't know their classes, but I know that the three will be from the same class because I created these children, right? So the marvelous part here is that once you create the children, you can create a function that will force the representation of these two images and make them together. So you learn a way in the vector space to get the child and the original, and you calculate a form of putting them together in the vector space. So if they have some differences, you are going to change this space until they they are in the same position or close enough in the transformed space. So suppose that in the original space they are here and here because this is like a rotated version. But then I transform the two in the vectors. And then if I could see these in the high space, I would see these a little bit far apart. But now what I'm going to do, I'm going to change this vector space so that they are going to rotate and they are going to move and they are going to be in the same cloud, the same part. And then if I do this for many forms, I'm going to have these chunks of data of children and mother. But as I do this for another image, suppose that the first one that I did was for like a Ferrari, a red Ferrari. And then I regenerate versions of this red Ferrari, and then they are here now. Now, suppose that I have a blue Ferrari, but I don't know. They are Ferraris. I don't have the labels. So I start doing like these transformations as well, and they are going to be in somewhere in this space. But as I'm having these different versions, if the form that I use to represent them in the vector space is good, it's very likely that this cloud is going to be close to the other cloud. And they are going to touch each other. So this is what we do with self-supervised learning. And then now I can pretend that I know the label. I can, okay, you're going to be A. Label A. No meaning.
So you classify them.
But then now you can train a method that will receive label A and label B from another cloud, label C from another cloud, and it becomes a supervised learning without you even need labels. So this is what we do. So we start with the raw data. It can be text, it can be images. Then for us, it doesn't matter the kind of neural network that we're going to use to transform this data into vector. We do not need to find the best. We can use more than one and combine them. So this is the second thing that's interesting. While people always strive for getting the best representation for the vector space, we thought, okay, I don't care about the best. I combine them. So when I combine, I can be much better. And then I do some way of optimizing the method in this way that I showed you, putting them closer if they are children and mother. And then I keep doing this for some steps until they converge. I'm going to give you a step-by-step. So let's start, for instance, with images. And let's say that we have 3 neural networks. One was created by Meta, the other by Google, it doesn't matter. But then for each one of them, I can represent the images. So one vector for each image. And then I calculate a matrix of distances. Quite easy. If I have 1,000 images, it's going to be a matrix of 1,000 by 1,000. As I said, I don't care about finding the best. I just have the different distance matrices of all the pairs that I'm analyzing. And then I average the distances. Simple enough. Because I understand that if the vectors are good, they represent the image in a good form. And then when I calculate the average, it's going to keep the points that are most distant in this way and the points that are very close in this way. So I have more than one backbone, as we say. We calculate the distances, we have these different distance matrices, and then we combine them. So this is the starting point. So this is like, you start with like 3 neural networks, any neural networks, find the vectors, calculate the distances, then you have the matrices of distances, and then you average them. Just that. And then, as we want to develop this, we combined some of the networks available in the literature, and just to show that the combination improves, you can see that the average is better than any of the other methods in isolation. So our hypothesis was right. So you do not need to find the best. You can get some of the good ones and combine them. But now comes the most interesting part. Pretty much everyone that worked in this kind of problem before, when they did clustering, finding the groups that are similar, they always attributed a point to a cluster based on a specific criteria. we thought, okay, but perhaps I don't have enough knowledge at this iteration to attribute this point to any of the clusters. So what if I abstain from not adding this point to a specific cluster at this iteration? And here you can see some examples. Suppose that I'm clustering, and then I have these groups there. All of the black points, for instance, or the darker points in that cluster above the yellow one, I might say, okay, I'm not sure enough if they belong to this particular cluster. Or to that one on the right, the orange one, I might not be sure if it belongs, based on the distance criteria. So the idea that we started here is, let's cluster, but if only 20% of the points are below the threshold of attributing, that's okay. That's the number that we are going to work in this iteration. But then the next iteration, we can have more information and do the attribution. So this is what happens. So in the first iteration, we start doing the clustering, and then we have lots of black points that I'm not sure if they should belong to a specific cluster. Here, for instance, I don't know if I should have one big cluster or like 1, 2, 3, 4, 5, 6 clusters there. I don't know. I don't have this information yet. So I abstain from clustering these points. And every time that you see a point, that I abstain it. But then if I can do that in different iterations, I can have a note for each point how many times it belonged to a specific cluster. So if it keeps belonging to the same cluster across different iterations, then I'm more sure about this point. If it's always a black point, that's a point that I'm not sure anytime. So perhaps it's not a good point for the idea that I mentioned before to use this for the part of supervised learning. So that's the kind of insight that we had. And then we do this for different iterations with different parameters in the clustering. And in the end, we have like the points that converge. Then you can get rid of the blacks. And then you just stay with the ones that got some label. And then with that, it improved a little bit more the results in terms of the literature to identify people in images. But then we also discovered that the learning rates, or how do you do this learning process, it needs to be adapted over time as well. So we proposed a policy to, at each iteration, alter a little bit less. So when you are learning something, suppose that you want to get to a minimum. So suppose that you have a function, it's a convex function, and the convex function, the minimum is here, and you start here. In the beginning, you can give like large steps, but as you are approaching the minimum, it's not good to give a large step because then you can like overshoot. So what we do in the beginning of the algorithm, we can give like large steps, and then as we approach the minimum, we give smaller steps. And with that, we can improve the algorithm as well. And here is the magic that I mentioned before. How do you put the children and the mother that I created close together? So you do this with math. So for everyone in the training set, in a group of images that you're training, that you create these representations, you force them to be closer together based on this product of F and P. I'm not giving much details here because it's like an optimization thing. But the other idea is that we can also do that for the examples that are more difficult. So the examples that I mentioned, that sometimes they belong to a cluster and sometimes they do not belong to a cluster, we can focus on them, and then they are going to be more interesting. Suppose that you want to separate cats and dogs. Suppose that all of the images become points in a vector space. So you have a bunch of points here, a bunch of points here. As we are talking about cats and dogs, they are separated. But where do you put the separator? So points here, separator here. But what are the most interesting points to learn the separability? It's not the one that's far away, and it's not the one that's far away. It's the ones that are close to this area of separation. So this is what we call, that's what we call hard examples. And then this is how we do it. And as we do that, we got the state-of-the-art results, even better than solutions using labels. That's the thing. It's very powerful to get one point and generate children of this point and force them to be together. All right. So here you have some examples of the method working. So you look for that particular guy in different cameras, and you want to see in different cameras if the top results are good, but we also needed explanations. So the red parts are the most important part of the image. Use it to take the decision. Then you can see that in this case, the blue shoes and the blue backpack or sack in his hand was the most important. But when he was like looking at the camera, it was more important the face. You can see that in this image here. But sometimes, depending on the light, it was more spread out. You don't know quite sure, but it is that person. Okay? So when you look at the maps, you understand if the person that you are looking for is exactly the person that you are looking for. Sometimes you have errors, but you can understand the errors as well. And then when you look at the maps, they look like this. They look like more green. So when you see a result like this, the method is much more confident. It's blue and red. When it gets an error, it's much more green. So you quickly see that, okay, it sorted the people there this way, but it's not sure. So you can understand what's going on. So this is the kind of thing that we give the experts when they're looking for someone. And everything that we did here, as I said, it was like working with like the scale of thousands. But then we wanted to do in the scales of millions. But to deal with millions of cases, it's quite complicated because the neighborhood computation or the matrix of distances is squared, O(n) squared. So what do? We start doing the same thing, but instead of doing with all of the points, we sample them. We sample them equally in this space. And we show that that's enough, as long as, in the end, instead of training the network to learn with the pseudo-labels in the traditional way, we train it differently. So what I said before was I have this cloud here. I give like a letter A for a pseudo-label, letter B for a pseudo-label, letter C for a pseudo-label. So I have 3 groups, A, B, and C. And then now I train a network saying, okay, the classes that I'm interested in is A, B, and C, separate them. So this is what I did before. Now, what we're going to do is a little bit different because I'm going to work with just a sample of the points. So what we introduced here was something like this. I'm going to train 3 methods. One is going to be separating A, B, and C. The other is A, B, and C. The other is A, B, and C. All of them will separate A, B, and C. But the first method trains to separate A, B, and C. But when I evaluate this method, I evaluate with the version of the second solution. So it's like training cats and dogs. Instead of having one method, I have 3. But then I use the first one to train cats and dogs, the second one cats and dogs. So I have the method that I can ask, is it a cat or a dog? But then when I evaluate images from here, instead of asking here, I ask here. And then instead of asking this one from this method, I ask the other method. So what I'm going to do is like that. I train with X and Y1, but when I evaluate the first method, I do with the Y2. So what I'm saying is that if I have the examples of A, B, and C, if I sample the points here, it's going to be a different sampling when I have A, B, and C for the second method, and a different sampling for A, B, and C of a third method. But if they're learning actually something really good, I can switch the labels and they're going to still give the answer. That's the idea. So example again, cats and mouse. I have 10 cats, 10 dogs here, other 10 cats and 10 dogs here, another 10 cats and 10 dogs here. So I have 3 classifiers of cats and dogs, but I don't know if it's cats and dogs. It's A and B, okay? So I train this first classifier, but instead of using these images now to test it, I test with this one. Then this one, I test with that one. So one method is teaching the others. That's the idea. So this is something that we call cross teaching. And it helps a lot in the process of training. It's called cross-teaching, co-training. And then when you put everything together, it's like this, forcing the examples to stay together. Here is the example of the random sampling. It's really random. Feature space, originally all of the points, and I just get one region, and I randomly pick some of them. And I still do the matrix. And when I have 2 points like that, I can decide if they are going to be part of the sampling, the green part, if they meet a specific threshold. So in this case, they do. For 0.25, they do as well. And it depends on what I choose. So this reduces the complexity from, it was, in terms of memory space, it was n squared. Now is kn. K is much smaller. K is the number of points that I keep. It reduces the complexity of the time. It was n cubed to do all of the algorithm, and it reduces to n squared log n, which is much faster. And then at the end, you have a much more effective algorithm, which allows us now to evaluate 250 hours of video in about 6 hours with one GPU, which is quite good. If you have more GPUs, you can be faster than that. But from 250 hours of videos to 6-7 hours, it's quite a feat. And here are some examples of the clustering. The code training, as I said, you train one method, and then when you test it, you test it with another, and then you test with another, and with another. So the idea is these are the different methods that we learned, but when you test the labels, you're going to see that they are helping the other method to be more effective. And we showed that if you use like only 25% of the data, it's already enough to get a good result, not only for the images, but also for the authorship. So again, here are some examples of the good classifications, successful cases. On the top, you have some examples, successful case. In this case, it changed what I said before. For instance, here you have quite a confidence, blue and red, but it's a wrong case. So it's wrong with high confidence. And this is the time that we need to pay attention, because when something is wrong but with high confidence, that might be a problem. All right, so we did the test as well for cars, vehicles. It works okay. It's not as good as for locating humans, but if you can get a good view of the vehicle, you can find them. And for future work, we are now thinking about integrating all of this to causality, which is the second topic that I'm going to show you. And also to understand a little bit more the relationship between a person and a car and a vehicle, because right now we analyze all of them separately. So suppose that you have a bank heist, you have an image of a suspect, and then you also have an image of a vehicle that the suspect might have used. We do the search separately. But they form graphs that in each of these nodes could be like a camera, they form a graph that could be used to help us locate better. For instance, if this person went from camera 1 to 2, 2 to 3, 3 to 4, and it used the car, it's also going to be 1 to 2, 2 to 3, 3 to 4. But as we do the separate analysis, we don't know the path in the graph right now. All right, so let's change gears for the second part, which is going from correlations to causality. And the work here was motivated by the Turing Award winner Julio Pearl, who focused much of his research in finding causal links. And he even published a book that's called The Book of Why. If you don't know this book, it doesn't need like a hard math background. It's going to be a very nice reading. I suggest you to read it. It gives you quite some ideas about how the world works. So the Book of Why. And why we want to do causal analysis is because when we look at something like this, we want to really, what's going on there? The red guy is really helping to push the truck or no? So if you upload an image like this to ChatGPT and ask ChatGPT to describe it, it's very likely, I didn't do this test, but ask ChatGPT if the red guy is helping to push the truck. I don't know if it's going to answer that, because it's getting quite expressive nowadays. It's getting better. But what we want to do with the data is this. We really want to find what's causing what. So when we think about the importance of causality, normally we think about 3 levels, according to Julio Pearl. The first level is about what you see. So do you see any pattern? Do you see any connection? So when you look for connections, when you look for patterns, this is basically what we have nowadays. That's the best that's out there. We are really good at finding patterns with the AI nowadays. We can read license plates. We can identify people. We can detect diseases quite nicely, because we are talking about correlations. We are talking about data that's connected. But then when we move to the second level of this ladder, we are not quite that good yet, which is doing. So doing is about when you do some intervention. So what happens if I do this with my data? What happens to the patient if I give this patient double of the doses of the medication? And the algorithms in machine learning and AI nowadays, they are not that good yet at this level. And they are even worse when we go to the next level, which is imagining. Imagining is when we do counterfactuals. Humans are pretty good in imagining. So we can imagine alternative careers that we could have chosen. Or if I went yesterday to a bar and I got involved in a fight, I could, when I go home, imagine different ways that I could have worked out the situation. So we are pretty good in imagining, but AIs, they are not yet. So what we do in the research with causality is we are trying to go from level 1 to level 2 to find the causal link. And then if we do that, we can do some intervention. So this is where we are now. Level 1 is about associations. Level 2 is about interventions. And level 3 is about imagination, counterfactuals. So the causal hierarchy theorem, in these 3 levels, we have seeing, doing, and imagining. They are fundamentally different. And they do not collapse into one another. They are different. One thing is about finding the pattern. The other is, once you find the pattern, what's the causal link? And then once you find the causal link, what's the intervention? And then if the intervention does not work, what could you have done differently? So this is imagination. And then let's see one important area that we are using this. We are working with this for the Brazilian pre-salt fields. Here in US, you have lots of success cases of oil exploration, but normally they are onshore. Onshore, it means on the land. And one thing is exploring oil on the land. The other is exploring oil on the sea. So Brazilian pre-salt fields, we are talking about oil that's like 10 kilometers down the ocean. So everything there is going to be different. The physics, the geophysics, the rocks, they're going to be different. And you cannot like look there and do like some seismic to understand the connections of the wells. You need to discover this based on sensors. So we need, at first, we want to find connectivity. And yeah, parenthesis. Do you guys know how oil is produced? So it's not like in the movies that you just dig a hole and then the oil pumps. No, it's not like that. This is nice for the movies and someone does this in the farm and then gets rich, right? No, oil, it comes up if you put something down. So it's normally inside the rock that's very porous. So in order for this oil inside this rock that's porous to come up, you need to push something into the rock to create the pressure to make the oil coming out. So normally when you explore oil, unless you are in the Middle East, which is like you dig a hole and the oil comes up, normally what you do, you have like one well that's called injector and the other well that's called producer. So if you want to produce oil here, you're going to introduce some material here. Normally it's water or CO2. Okay? So introduce gas or introduce water, and then when you do this, it pushes the properties down the earth. So it changes the pressure, and this pressure pressures this rock here with the oil, and then it goes up because this is a producer well. But normally we don't have one and one. We have dozens of producers and dozens of injectors. And the process of finding one injector is just like the process of installing one cell phone antenna. You want to cover the most possible. But when you look at where to install a cell phone antenna, you see everything. And you know the area. But when you look at where to put the injection well, you don't know much because it's down the earth. So it might have like a failure there, a geological failure. It might not be connected, or it might be connected by like some sand, soil, and then it's going to be like quite sensitive to changes in the injector. It's quite different. So what we have is a series of injections and a series of producers, and then instead of just looking at how correlated each pair is, we want to find really which injector is doing the most influence in a particular producer. That's the question. So this is the causal link. And then we might have 3, for instance, injection wells causing the producer here. One might be 50% strength, the other 25, the other 25. Okay? So in addition to just find the causal link, we also want to quantify the link. And of course, this is important because if I find the connection, as you see there, we have 2 injection wells, and then I inject something and they're helping to produce on the other side. If I find their link and if I find the strength of each one, I know if it stops producing the amount that I wanted, what's going to be the change that I can do to the injection so that I can produce more. So this is economics. So causality matters, and it's difficult, of course, because one thing is to find that something is correlated. Like during summer, we have an increase in ice cream consumption and also an increase in drowning. And then a smart person might say, yeah, let's stop selling ice creams because people are eating ice creams and they are getting drowned. Of course not, because what happens is that in the hot summer, people go to get more ice cream, and they also go to swim, and then as more people go to swim, more people get drowned. So that's why it's important to find the causal link. And when we think about causality, we have the causal inference that estimates the causal effects and counterfactual analysis and for informed decisions. Like this is going to be a graph. A is causing Y based on the data. And of course, we need to do some assumptions about the problem. And we can do this from different techniques in the literature called average causal effect, conditional causality, individual cause effect, and so on and so forth. And then we also have one thing that's called causal discovery. In here, we want to identify the causal relationships of variables from observational data. So based on the data that I observe, can I have some information about the causal links? So everything that we do, it's based on the right. Because the only thing that I have about these wells under the ground is a set of sensors that I put there to understand the pressure, the temperature, the amount of water it's producing, the amount of oil that's producing. Those are the things that I look at, time series for the production. And on the left is when I have some extra information about the problem. So general framework for causal effect estimation. So you have a causal query. You are asking if A causes B, for instance. Then you create a possible graph. Then you observe the data. And then you come up with, OK, A and B, they are connected, but they are not causally connected. Or A is causing B. Or B is causing A. Or is just spurious. So this is called causal effect estimation. And then the challenge that we have in the field is like, as I said, we have time series. And it's a very dynamic system because when you measure it, then the second later, it already changed because you produced more oil and it changed a little bit the properties. So if you produce 1,000 barrels of oil, the pressure is going to be different after you produce that. The quantity of oil in the reservoir is going to be different after you produce that. Everything changes. And you need to account for that when you do this analysis. And of course, when you have this dynamic setting, you also have some confounding factors that they might be hidden. And one hidden factor is like this that I showed you. Here you have an example. The hidden factor here was the hot weather. So how can you find that? So what we do, we can follow two different paths. Well, we can follow different paths, but here we follow two of them. We have the treatment, which is how much injection I'm going to have. So this is called treatment. And then we have the outcome, how much oil I'm going to produce based on this treatment. So for this connection, I want to find the causality for the connectivity. So I want to estimate that. And I want also to do causal inference to measure the strength of that connectivity. So the first part I can do with an area called causal abstraction or causal invariance. The second one I can do with time-varying causality, or one recent thing called blessing of multiple causes. So question, association or causation? So like this meeting, we found this correlation in the data. So every time that we have some people with shaved heads, the sales increase. So let's have every employee of the company to shave their heads. And then the sales is going to skyrocket. Of course not. So the boss might think one thing. Others might have thinking that shaved heads, it's like when the sales get increased, people get excited, and then they decide to shave their heads. But the boss thinks that when the employees shave the heads, it increases the sales. Or others might think, yeah, it's not even connected. So we need to look at the data to separate this. Some observational data can generate multiple causal diagrams. So how do we do? We, instead of working directly with the data, which is very noisy, time series, and it's collected like every second or every minute, it depends on the sensor, we describe this time series in an interval with some features. And this description might not be with like machine learning, it might be with some knowledge of the expert. So we have here the possibility of using low-level micro variables, so low-level features, and high-level features. And then with this, we reduce the experimental effort to understand the mechanism of the connections. So macro variables thought of functions of the micro variables. So the macro is on top of the micro. Challenges. Causal information from invariance may preserve the necessary information for the task. So what we want to do is to analyze in intervals so that in that interval it doesn't change much. The strategy here is to create features from invariant phenomena, things that do not change in that particular time in the reservoir. So what do we do? Physically connected wells, they have a persistent causal footprint over time. So think about this. I have an injection here, and an injection here, and a producer here. So whenever I change the injection here, I have an effect here, but here it's not always. So what I'm saying here is that when they are really connected causally, if I do some changes in one of them, it will always reflect a change in the other that's affected. So physically connected wells, they will leave a persistent footprint. And while the others that are not connected, they are not so stable in terms of these effects. Connected pairs, they behave differently from unconnected pairs. For instance, connected pairs, they have like a structured and invariant signals. While unconnected, they might be randomly showing some interactions, not all the time. So this is the thing that we want to find. So the diagram looks like this. We start with the raw signal, time series. They vary over time, like for every minute, for this well, this well, this well, what was the pressure? So I have a series of like all of the measures of pressure, all of the measures of temperature and things like that. And then I calculate these features that I mentioned. And with that, I do different tests because I can have these different windows in time. And for all of them, I check if A is causing B, A is causing B, A is causing B, A is causing B, and then it's a process of like integrating them. So we start with statistical features. We look at the dynamicity, human operators, and potentially unmeasured confounders. So we have a two-version approach inspired on causal feature learning. First thing, statistical feature, phase one, we look for the micro variables. What's the fluid injected? What's the amount of water? What's the amount of gas? Is it the two together or separated? Then what was the production at the end in the producer? Because we are always analyzing in pairs. And then did the operator close the injection for some time? This is called choke. All of these come as features for my micro variables, like this. And then, as I have these features, each possible node here, we'll have this set of features, which is a vector. And then with this vector, I can use some methods from the literature and calculate mutual information, power spectral density correlation, conditional mutual information, the distance of these vectors. All of these will be integrated along with the features that I just calculated. So with that, we have pairwise features. For instance, fluid production and choke are the micro variables. This is a vector of 3. And then each point here is a vector of 3. And then for these points, pairwise, I can calculate like those measures in the middle. And surprisingly, but for people in the oil area, one injector can also influence another injector because it's physics. So if you have if you dig a well here and you dig a well there, the two are injectors. They are supposed to influence just the producer. But if you inject something here, as it's everything like rocks in there, it might somehow, in a less in a weaker form, but it can also influence this injector here. So that's why we put the 3 points there. And then in addition to the statistical features, we also have the physical features. This is with the domain knowledge. We have the reservoir engineers to help us in this case. So we look for their help to understand the porosity. How is the porosity and permeability of the soil there? What is the fluid dynamics of things are coming this way to this way because this is higher up. And this well is like 2 kilometers down, so it's very likely that if it's water, it's going down. So we look at that, and then we combine the statistics and the physics together. And the contribution in our case here is if causal mechanisms are invariant, if the features can isolate physical connectivity, it allows to build more reliable operation decision tools, providing insight and better explainability. So the general framework that we are working, and the company here is Shell, we started working with synthetic data for which we have total control. And then we simulated some linear relationships, and we pretended to have some injectors. We pretended to have some shock variables. Then we moved it to a real simulation of Brazilian pre-salt. Here, it's still simulation, but much better than simulated data set. And then we moved on to the real case of Brazilian pre-salt. We are working now with 2 big Brazilian fields to understand their causality. And it seems that it's working nicely. Of course, it's impossible to know exactly what's going on because the only way that you can confirm the causal link is when you inject a tracer in one injector, and then this tracer appears on the other side. So suppose that you have water injection. You can put some colors or some chemicals in this water. Then when you inject this water with a specific chemical, when this specific chemical appears on the producer, you can confirm, there is a causal link here. Okay, so this is when we confirm that our guess was correct. But so far, we already confirmed some connections, and some are still pending. So some connections that we proposed, we still did not find any tracer. So this is what looks like when you look at the oil field. The first one is a work that we had in Nature in 2022, I guess, 23. And then recently we have work published in Frontiers of AI, which is the one on the right. And when you look at that, when you see anything that's red or blue, it's already a confirmed connection. When you see something black, it's something that we found recently, but it's still not confirmed. The difference is that the paper that we had in Nature in 2023, we needed about data for 1 to 2 days to analyze. Now we can do that with less than 5 minutes data sampling. And this is how it evolves. This is another nice thing. One injection might be well connected to a producer in this month, but 2 years from now, after producing a lot of oil, it might not be significant anymore. So the connectivity and the causality links in the field changes over time. All right, so to summarize this, this is a recent work that we've done, published it in IEEE recently. And in this case here, we do multiple analyses at the same time in different points of the time series so that you can come up with like a voting system in the end to check if there is any causal link. And then this is the last one presented in Rio 3 weeks ago in a workshop in iClear. We decided to put everything in a large language model. So we decided to create an LLM so that the operator can come up with something like this and write, it's impossible to read here, but it's like, is there any causal link between well 15 and well 18, for instance? And then we run under the hood the causal link analysis that we implemented with an agent, and then the agent gives the answer to the LLM, and then the LLM prepares the answer to the user. And the user might, okay, as you found this causal link, what's going to be the forecast for this well for the next 12 months? And then it can also calculate the forecasting for the next 12 months. All right, so in summary, we want to find this connectivity because it helps you in the decision-making process. It's much better to work with causal links rather than correlations. And that helps you to go to the second step, which is, okay, I found that A is causing B, so if I inject water here, I'm going to produce an amount of oil here. But since last month, this well here is producing like 20% less than it used to. What can I do now? So now you can, okay, what if I inject 10% more water, or 13% more water, or 30% more water? Is it going to recover this 20% that I just stopped producing? And then you can do these simulated questions before taking decisions based on the data. And an important aspect that I didn't mention is you cannot just inject more to produce more. Because if you inject more water than the adequate to change the pressure there, the water that you inject, it's not only changing the pressure, the water will itself go to the producer. And then instead of producing oil, you're going to produce water. So the dumb question here is, I produce 100 barrels. I want to produce 200 barrels. Okay, let's double the amount of water here. No, this is not how it works. Because if you do that, you're going to produce water on the other hand. So this is something. This is why we need to carefully calculate this. And here are some more results. The Brazilian pre-salt field. Here we have also the confirmation by the tracers, red and blue. But you can see that we have a bunch of others that we found, the green ones that are still not confirmed. You can see that when we confirmed we found it, that's good. But we have some green ones that were not confirmed yet. For instance, like the blue one, I3 here to P4. We have no confirmation for that yet. And even I3 and P2, we already confirmed that I3 is changing something in that one, but we did not confirm that I3 is influencing P2. There is no confirmation yet in terms of physics. Okay, so wrapping up, we have situations in which we need to do continuous learning. All of these scenarios adapt. They change, so we need to adapt to them. So the conditions are dynamic. We not always have the label, so it's open set. And we need to produce everything that's explainable. So this is with XAI involved. We deal with different sensors. Sometimes we deal with big data, sometimes with small data. Some of these sensors, they fail. So imagine we are talking about 10 kilometers underground. some sensors will like fail for like 1 hour or 1 minute, and then they come up again. You need to be able to see that's a failure and not something that's actually measured. And you have lots of missing variables most of the times. So this was it as part of this talk here. I hope that you have liked it. I can answer some questions. And if you want to follow me on LinkedIn, this is the QR code. Thank you. All right, so any question? Please go ahead.
About your work on explainability.
Yeah. So let me give you an example of why this is important. Some time ago, about 3 months into the pandemic, we decided to collaborate with folks in the biochemistry and pharmacy to develop a new test for COVID. And you all know, you all lived through it. It was quite nasty to do the test in the nose, and yeah. So we thought, okay, what if we could do a test that is like just like a sample of blood, and then you can have this answer. And then we started collecting data from all over Brazil for people with and without COVID. We collected like 1,000 patients. And the idea was you draw a sample of blood, you separate the plasma of the blood, and then the plasma goes to an equipment called mass spectrometer. And the mass spectrometer is going to give the molecules that are present in that sample. And the idea is that if you have COVID, the molecules will have a different signature than when you don't have COVID. Everything was nice, collected data, 3 months into the research. First result, 96% separability. Wow, PCR is 90. So the gold standard is 90, and we starting this problem now with AI, it's going to be like 96. Something is wrong. So we have a rule, and it's a rule that I teach to all of my students. In AI, if something is 0% or close to 100, go back to the calculations because it's wrong. So we separate the molecules, and we proposed the molecules to the pharmacy school, and we asked them, okay, can you check if these molecules are valid, because the result is like quite nice, it's 96%. And then they came back to us and said, yeah, you know what? You found a very good way of separating people that take antibiotics and people that do not take antibiotics. Why? Because in Brazil, pretty much everyone with symptoms, they would go to the hospital and they would start with a kit of antibiotics. And then the ones that stayed at home, of course, they were not taking antibiotics. And we programmed the algorithm to separate the two groups. And what was the best molecules to separate them? Antibiotics. Then we needed to teach the algorithm, oh, here are the classes of antibiotics that we do not want. So let's see the second round of separations, 91%. So it's too good, right? And we went back to the pharmacy school, and then, yeah, you know what? You found a very good way of separating people that drink coffee and people that do not drink coffee. Why? We're talking about Brazil. Brazil, everyone drinks coffee if they are not in the hospital. So people that stayed at home during COVID, they were drinking coffee, and the ones in the hospital, they were having antibiotics. So then we taught the algorithm, okay, here is like the molecules of caffeine, so you should not focus on that. And we did this for some time. How we do it? Random forests. So we separated the groups based on these vectors of mass spectrometry. And then with random forests, we found the variables with highest separability. Then with that, we identified the molecules and proposed it to the pharmacy school. They went to the books and they said, okay, this is caffeine, this is like antibiotics, and so on and so forth. And then we kept doing this until the algorithm converged, and then at the end, it was like 88. So we were satisfied with that. It was like licensed to the government. They used it, not in high scale, in large scale, because it required the mass spectrometry, and of course, not everyone has in a clinical test, but it was quite nice. So explainability. We think of the problem since of the beginning in a way that with the help of the expert, we can understand what's going on. So as I said here, it was looking at the vectors of the mass spectrometry, selecting the molecules and asking the experts, this molecule, does it have any meaning? When we're talking about, for instance, identifying if a document is fake, I want to look at the document and see what was changed to understand why it was fake. If I want to identify, there was another problem that we worked with, and now it's a startup. We wanted to predict if a person was getting blind based on an image of the retina. People with diabetes, they might have a complication called diabetic retinopathy. So it's about 1/3, 1/4 of the people with diabetes, they can have this. And some of them will go blind if they do not treat it and if they do not follow quite closely. So we wanted to do the analysis of the retina images and show the doctor that that person needed careful attention. So our first solution was we were giving the doctors, okay, this is an image of the retina and this patient needs attention with 88% of certainty. And the doctor said, yeah, so what? I'm not seeing anything in the image. You should show me. And then our next round was, okay, so this patient needs careful attention with 88% chances of complication because of this region and this region in the retina image. And then when the doctor looked at it, oh yeah, you were right. I was not seeing this like a hemorrhage just starting here. So you need to think of explainability not as something after the fact. You need to think of it doing the whole process of data capturing, data annotation, and decision making. So this is the kind of thing that we try to do. It's not easy. Explainability it's like a long way, but it's important.
Wonderful. I've got a couple questions from the viewers at home.
Okay.
I will start with one. So this is in regards to the clustering. Mm-hmm. Are you assuming a hard assignment of each perturbed object to a single cluster, or do you allow a soft probabilistic assignment across multiple clusters?
That's a very good question. The hard assignment, in our case, we did with hard assignment. So to explain to everyone, when you do clustering, one point might belong to one specific cluster. So it's a 0-1 belonging. So if you have 3 clusters, if I associate with one, the other 2 will be 0. Or it can be probabilistic. So it can be 50% belonging to this one, 25 to that one, 25 to that one. So in our case, to simplify and make things faster, it's hard assignment.
Hard assignment, okay. Follow-up, or different, another question, but different topic. Is regarding like the oil field, is there a Gaussian process layer in the model, and is the intent that it only captures spatial function correlation rather than causal structure?
That's a good question. We used Gaussian process for the simulated data set, the first one that we worked with. We worked with some Gaussian simulations, but the other two, no, is directly modeling on the data, the way that the data comes.
Okay. And the follow-up to that is Kringling, I'm pronouncing that wrong, is a universally used method for measuring spatial correlation, which could be viewed as causal, but it's not here. Is there a reason?
We did not explore it yet,
Okay.
but we are in the new studies that we are doing. We are exploring like many different methods, like Granger and many others, and then the idea is to combine them.
Beautiful. Well, thank you so much.
Thank you.
Does anyone have any other questions, further questions? Come on, don't be bashful.
Thanks a lot, guys.
All right.
Thank you.
Let's give it up to our speaker. Oh.
I have one that's not algorithmic at all. I have a question that's not algorithmic at all. It has to do with the oil field. So I'm just wondering, when you inject a tracer, what's the time delay between injection and discovery? Is it a day, an hour, a month?
That's really nice. It really depends on the reservoir. Sometimes you inject a tracer and 6 hours later, it might appear in a specific well. Sometimes it's going to be 3-4 days. It really depends on the rocks down the earth. Yes.
Order of magnitude.
Yep. Thank you.
All right. Well, I appreciate it. Everyone, thank you so much for attending today. Again, like this wouldn't be possible without IEEE. And our speaker, fabulous. Really appreciate him.
Thank you.
Making a trip to Madison, Wisconsin from Brazil. So.
And I got lucky. Very nice weather. Thank you. Thank you, guys.
Thank you. Thank you at home as well.